Hi there, welcome to this presentation presented by ERL Phase Power Technologies. We're located in Winnipeg, Manitoba, Canada, and today we're going to be talking about a subject on how to analyze power system faults. The name of the presentation is called A Guide to Digital Fault Recording Analysis. My name is Joe Perez. I'm an application engineer for the company. My contact information is in front of your screen, so please feel free to contact me after this presentation is over. Here's the outline. We will be discussing the purpose of fault recording, on why we use fault recording to analyze faults. Then we'll be talking about the oscillography that microprocessor relays and digital fault recorders offer. We will also be talking about the differences between the fundamental RMS versus the true RMS waveforms. Then we'll be talking about how to use symmetrical components to decipher power system faults, and finally we'll be talking about how to graph ground faults in the RX diagram. The soft harmonic presentation is not on this video. So if you're an experienced power system engineer and you look at this waveform, you probably know what kind of fault this is. If you don't know what kind of fault this is, you are in the right place. This presentation is going to teach you how to analyze faults and how to determine what kind of fault it is by just looking at the waveform traces of the voltages and currents. Here is another trace of voltage and currents on a 345 kV system and a 115 kV system as well. And this is another kind of fault, and as we can see, this kind of fault behaves in a different way. We could easily determine what kind of fault it is by using symmetrical components, and that is what we will be discussing in this presentation as well. But first we need to cover some basic fundamentals and some reasoning on why we do fault recording. So there are event analysts who investigate system failures. These people investigate relay operations and system events, and they analyze the behavior of the power system and oversee the proper and improper operations. They can see why certain relays operate correctly or why system equipment did not work correctly. Investigations of this manner result in improving the reliability of the system. As a result, we can always redesign things, and also we can recommend corrective action, and at the end we can always save money. So what does it take to analyze these events? Well, unfortunately, analyzing power system records and faults is not an intuitive process. It requires a lot of system protection knowledge, and it requires knowing what sorts of protections are for the different protection schemes. It requires knowing the different power system elements as well. For example, we have breaker operations that need to be known. And an example of this is a breaker. A breaker behaves differently and it opens at different times. So if we know how long it takes a breaker to open, then we know that such breaker is working correctly. Usually a breaker will the time delay of a breaker to open its contacts is usually 3 to 4 cycles, depending whether it is an insulator type or oil type. Now if a certain breaker is opening in a longer time than this, then we might have a problem. And the traces can tell you when that breaker open or close. And at the end, analyzing faults is really a matter of practice and experience. After years of doing the same thing, you are easily going to recognize the same events, and you're just going to get much better. And then, of course, with more experience and more practice, these people are hard to find. So for new people getting into this kind of field, the purpose of fault recording needs to be known. Also, the components of the oscillography also have to be understood, and then we'll recommend knowing the sequence of events, what that is. And using symmetrical components to decipher faults is very critical, since microprocessor relays and digital fault recordings offer these capabilities. And at the end, of course, using what the software tools give you is really important. So the purpose of fault recording usually falls into these two main categories. One is recording of power system events, and the other one is to monitor power system behavior and protection. When we talk about the purpose of fault recording to record power system events, we talked about recording the voltages and current magnitudes of a certain particular element. Also, we need to capture the time of fault. This will tell us exactly when the fault occurred. If it is synchronized, it will tell us the synchronized fault, of course. And we can also analyze power system swings that usually are seen in the power system. We could also analyze abnormal instrument transformer behavior, such as CT saturation. Another factor is the effect that DC offset has on the relays, which is just the inductance, how high the inductance of the system is. We could also analyze CCVT response, especially for line protection relaying. The CCVTs will affect the voltage waveforms during faults. So this is very important to analyze those records. The second purpose of fault recording is to pretty much monitor the power system performance during an operation. For example, the failure of a relay to operate as intended needs to be reviewed. Why certain relays did not operate as designed? The waveform oscillographic data captured by the relays and microprocessor DFRs will tell you exactly what happened. Also, another reason why we want to do fault recording is because certain relays would operate during external faults. For example, bus protection or transformer differential protection sometimes operate during external faults. And the oscillographic data can tell us what happened during such event. We can also analyze line reclosing and the times that it took to open the breaker. Breaker failure analysis is also very important. When we talk about the components of oscillography, we usually talk about the record lengths, the time frames, and the fundamental RMS versus the true RMS waveforms. And also we talked about the sampling rates that relays and microprocessor DFRs offer. For record lengths are classified as transient records and swing records. Transient records are designed to capture very fast events such as lightning strikes, power system faults, or switching events. Some of these events are very short-lived, so they're between 16 cycles or less. The other type of record, this is a record from a microprocessor relay. This is an external fault, but this is just an example of how a relay would capture an event. The other type of record is what's called a swing record. These records are usually sampled at a slower rate, and they are designed to capture the dynamic response of the power system. For example, what happens to generation when there's a fault on the system? The system starts to oscillate, and sometimes the generation would not respond. The frequency will go down or up depending on the system behavior. So swing records can provide us a good idea of an overall system behavior. This is a record of a power swing. The trace on the top is the transient record. The trace on the middle is the transient record, but on a smaller time frame. Now the time frame is on the middle, and the third trace there is 50 seconds. So the swing record is the last trace there, the third trace, and it has been shrunk to capture the entire event during 50 seconds. So we can see what the overall response to the power system is for this record. We can see that the voltage has dipped down there, and then you can use this record to analyze how generation would respond, and you can export this record and import it in a program such as PSSE. The other thing that we need to be aware of is the time frames. These time frames could be either cycles or milliseconds. Now this is very important because relay settings are usually set in milliseconds or in cycles. So knowing the interchange characteristics of these time frames is very important. When we talk about the fundamental RMS versus true RMS, we talked about two different things. The fundamental RMS are all the waveforms is the waveform containing only the 60 Hz. Now microprocessor relays operate in this manner. The reason they operate in this manner is because all the other frequencies have been extracted by using direct Fourier transform or a fast Fourier transform, and other manufacturers use the cosine filters. The true RMS is the waveform that contains all the harmonics based on the maximum sampling rate that such device would offer. Now electromechanical relays operate based on this principle, based on the true RMS. Now the problem is that sometimes the harmonics would cause electromechanical relays to misoperate. That is the reason why now microprocessor relays extract all the other harmonics. Now solid state relays would operate on the peak magnitude of the true RMS signal. So what we have here is, on the left hand side we have the RMS content of only 60 Hz, and on the right we have the true RMS content with all the harmonics. So we have the second harmonic, third harmonic, fourth harmonic, and fifth harmonic ratio compared to the fundamental. Sampling rates. Sampling rates are important if you want to capture more harmonics. For example, if you're sampling at 32 samples per cycle, the highest harmonic you can get is up to the 8th. Now microprocessor relays offer 96 samples per cycle, and it will capture all the way to the 25th harmonic. Now if you keep increasing the sampling rate, you're going to increase the frequency range and also your harmonic range. So digital DFRs can now do 384 samples per cycle, which will give you the 100 harmonic. Now if you want to go into power quality sampling rate, you're talking about 500 to 1,000 samples per cycle, which are necessary for power quality. Filter versus unfiltered records. This is very important. Now the filtered waveform is the waveform that contains only the 60 Hz magnitude. Now the unfiltered record is the one that contains all the magnitudes. So making sure that you get the unfiltered data records is very important, because it gives you the true response of the power system event. Sequence of events. Sequence of events will tell you, will capture all the digital signals that are coming into either a relay or microprocessor DFR. Now one of these sequence of events is the breaker status, which tells you when the breaker open or close during a certain power system operation. The 52A contact is a very low cost solution because it doesn't take very much to implement it. Now, using trip call surge detectors is a much better way to detect when your breaker actually received the tripping signal. Now, these coil surge detectors operate in less than 1 millisecond. And you can put this in series with the trip call primary and the trip call backup. This is a control diagram of how those trip surge detectors could be implemented. The 74-1 overcurrent relay there has some auxiliary contacts that could be wired to the DFR relay, and then we could capture the traces of such operations. So what we got here is an operation on a 115 kV system, and we have two trip call surge detectors. Now, trip call 1 and trip call 2 operated, but trip call 1 operated a little with some time delay, and that could be to the way that certain signal got there. So this needs to be investigated. Now to the most important and most exciting event here in subject is using symmetrical components to analyze power system faults. Now, if you haven't taken a class on symmetrical components, it is strongly encouraged that an engineer takes this class, especially if he or she is going to be involved in analyzing faults. Now, why is this important? That is because symmetrical components are the foundations to understand faults. Digital fault recorders and microprocessor relays operate and function on the fundamentals of symmetrical components. Also, familiarization with the phase representation of faults is very important because it tells you how the vectors behave during faults, and you can easily picture how these vectors work and respond to power system events, and then you can decipher what kind of fault that would be. So, for a phase to ground fault, if you have taken symmetrical components, we know that the picture on the left is the simplification circuit of that power system fault. So for this system, we know that you are going to see a positive sequence, a negative sequence, and a zero sequence components. Now C1, C2, and C0 represent the positive, negative, and zero sequence impedance. Now, for a phase to ground fault, we could see that the vector behavior there on the middle and right graphs. So, during abalanced conditions, all vectors are 120 degrees apart. However, during a phase to ground fault, all our vectors have changed. Now, this seems to be an A to ground fault. Why? Because for an A to ground fault, usually the voltage will collapse, the faulted voltage will collapse, but the voltage current will increase significantly. So voltage A phase here has collapsed, and current A phase has increased significantly. So we could determine that this is an A to ground fault based on the system behavior. Now, if we look at the real waveforms, this is an A to ground fault. Now, my voltage A has collapsed, and my current A phase has increased significantly. So, without the relay telling me in a text-based form, I am looking at the waveform, and I know immediately what kind of fault this is. So, when analyzing these records, you could probably determine what caused this fault. Phase to ground faults could be caused due to numerous causes and reasons, such as lining insulation failure, or some kind of boom truck touching the line, or who knows what, or a conductor has collapsed. So this is just some of the reasons that a phase to ground fault could occur. Now, if we look at the symmetrical components view, we could easily see what the content is for each sequence. Now, for a phase to ground fault, we know that all the sequences will be present. So, for a positive sequence, we could expect very high values, and so for the rest of the sequences. For this case, we can see that we have about 1300 amps on positive sequence, we have about 1400 amps for negative sequence, and we have 1700 amps for the negative sequence. For the zero sequence. And for my A phase vector, we see that it has increased significantly. So this is clearly an A to ground fault. For a face-to-face fault, things behave differently. So the symmetrical component circuit is shown there on the left-hand side, and we could see that for a face-to-face fault, there are only two sequences, positive and negative sequence components. Now, as far as the fault behavior vectors, we could see that for a face-to-face fault, the two vectors there are 180 degrees apart for A and C currents. And also for the voltage vectors, we could see that they have slightly been reduced. So if we looked at the waveforms, we should expect a very similar behavior. A face-to-face fault, we could see that the two voltages have slightly collapsed for B and C phases. For A and C phases, and A and C phase currents are 180 degrees apart. So when looking at a graph like this and you see these nice waveforms, you could easily determine what kind of fault this is. This is a face-to-face fault. Now, if we look at the symmetrical components as described by the circuit, we are supposed to only see two sequences, positive and negative sequence components. Very high values we should expect on this component. So we could see that for the positive sequence component, we have about 2200 amps on positive sequence and about 2300 amps on negative sequence, and about 2 amps on the zero sequence. So this is clearly a face-to-face fault. Now the two vectors on the left-hand side are 180 degrees apart. So this is clearly a face-to-face fault again. Now for a three-phase fault, three-phase faults are what's called symmetrical faults because they don't involve any other sequence but the positive sequence component. And for the fault behavior vectors, for the behavior of the vectors, we could see that for a three-phase fault, all the phasors are involved, A, B, and C, and for the currents, they increase significantly. And for the voltages, all three voltages are reduced. So for the voltage and current behavior, we should expect very similar things. So we can look at the voltage waveform here. All three phases collapse, and for the current behavior, all three phases is increased significantly. So based on what we have just discussed, this is clearly a three-phase fault. Now, as seen on the sequence circuit, we should only expect positive sequence components. So for this case, we have about 4200 amps on positive sequence and about 300 for negative and about 190 amps for zero sequence. So this is probably inherent to the system. Sometimes faults will evolve from a phase to ground to a phase to phase and then to a three-phase fault. So sometimes we see zero sequence components at the early stages of the fault. But then, of course, when it evolves to a three-phase, everything should only have a positive sequence component. Now, software tools are very important because it allows you to simplify things and it also allows you to visualize things better. Now, talking about graphing power system faults in the RX diagram, here's an example. What we have here is a line to ground fault, and the fault impedance for B phase is graphed there. We have also superimposed the line characteristics or the Mohs circles for this particular line. Now we have the RX diagram, we have the Mohs circles, and also we have the line impedance graph in this particular picture. So we know this fault is on B phase, and it's about 20-30% of the line. Usually the first circle there is about 80%, and for this case we have just inserted the quadrilateral characteristic for the first zone, but this could also be replaced by a Mohr circle, which is the circular type. So this tells you that the line fault was aligned to ground fault, and it was about 20% of the line, and this could be determined by the fault locator algorithm that relay or a microprocessor DFR will tell you. When analyzing differential faults, this is a differential view. Now for this case you have the IO min, the first slope and the second slope, and anything below that black line is the non-operate region, and anything above that is the operate region. So if anything went above that region, it means that certain relay operated. For this case it looks like the relay operated, and it looks like it was an external fault. So a review of the IO min settings might be necessary here, because certain faults are higher than others, and sometimes through faults can be really high and the settings might be too sensitive. So conclusions. To conclude this presentation, the analysis of oscillograms, it's very important, and it has proven to be very invaluable over the years. And of course, when we recommend changes into the design, or recommend changing procedures and then so on, we eventually are saving money to the companies. The other important thing is to train your new engineers. If you are experienced, take some time to explain some of these behaviors or how to analyze faults. At the end, you know that right knowledge supported by great recording tools leads to great event analysts, and at some point you might have job security. And that's about it. I'm concluding this presentation. If you got any questions, again, you have my information at the beginning of the slide, and I hope this presentation was very helpful to you.